I received several questions about the operator norms for matrices and how to use them in examples and how to compare them. So I wanted to do some examples of this. First of all, let's recall the vector norms. The LP norms in particular. So if you've got a vector v, well, the n norm, or I should say the p norm, is the pth root of the pth powers of all of the terms. We're of course most familiar with the 2 norm, the standard Euclidean norm, and the 1 norm, and also the infinity norm. Now, to interpret the infinity norm, really this just means, if you think about sort of the dominant term in the limit as p goes to infinity appearing most prominently, this is really the maximum of the absolute values of the terms. So it's just look for the biggest term is what the infinity norm is. Okay, so just a quick comparison here. We know what the circle looks like in the 2 norm. It's our nice round circle. But of course, the definition of a circle is it's the points which are distance 1 from the origin. If I do that computation with the 1 norm, well, 1, 0, and 0, 1, and negative 1, 0, and 1, 1, and negative 1, 0, negative 1 are all distance 1 from the origin in the 1 norm. But so is 1 half, 1 half, and so on. So actually we get this diamond as our circle. Moreover, for the infinity norm, these also have norm 1, but so does 1, 1, because the largest term is 1. This isn't the greatest drawing, but you can see that each norm has a different level set. So we have the set defined by this condition, or by this condition, or by this condition. And one might ask, what are the comparisons between them? For example, if I know the 2 norm of a vector, how big can its 1 norm be? If I know the infinity norm of a vector, how big can its 2 norm be? And you can see that looking in different directions, there are direct comparisons you can do by looking at the distance to the corners of the square versus the side of a circle versus the middle of the side of the square, and you can do the comparisons of the ratios. So what we'd like to do is have some results which quantify this precisely. Among those results is exercise 3.3 in Trefethen and Bow. So first of all, it asks us, suppose that we have a vector, an m vector, and let's examine its infinity norm and compare that to its 2 norm. And in fact, the claim is this. Okay, how can we prove this? Well, this is actually fairly straightforward because the infinity norm is simply the maximum of the absolute values of the terms in the vector. So if we consider, say, the infinity norm squared, that is, let's say that I is that maximum term, xi squared. Whereas the 2 norm squared is x1 squared plus x2 squared plus da 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 plus xi squared plus da da plus xm squared. So xi, if this is actually the maximum, that appears here, but so do other things. So clearly, you add a positive number to this positive number, it can only increase. So we have this condition, the 2 norm, the square of the infinity norm is less than or equal than the square of the 2 norm. Since they're both positive or non-negative real numbers, take the square root and you obtain the result. 3.3b is very similar. It's saying that the 2 norm is less than or equal to the square root of m times the infinity norm. Well, you can see already how this is going to work. First of all, it suffices to prove that this is true when you square it. So now think about what this is saying. This term here is the maximum element of xi. And if I take that term and square it, it's actually, let me write it that way. If I take that term and square it and apply that m times, well, x1 squared is less than or equal to xi squared. And x2 squared is less than or equal to xi squared, etc. All of the terms in x have absolute value less than or equal to the maximum, of course, by definition. So if I add all these up, that's, I should call these j since I'm reserving the letter I, that's less than or equal to adding up the biggest one, m times, which is this statement there. Now, things become more subtle if we consider the matrix norms. Recall, if we have A, which is an m by n matrix, in other words, A can be thought of as a map from Cn to Cm, then what we might want to do is consider the matrix norm, which is the supremum of the 2 norm of all outputs of A over the 2 norm of the corresponding input of A. In other words, consider all points on a given circle, all vectors on a given circle, and ask for each of those vectors in the output, where does it end up? Now maybe this isn't an eigenvector, so it's not stretched directly, but somehow its magnitude changes in addition to whatever else might happen. And so the ratio of this output to this input is what we're examining here. In other words, how distorted does the circle become in terms of its maximum radius to the original radius? If you start with x as a radius 1, then you're asking where does the unit circle go? It's distorted to some sort of shape. And the question is, well, what's the maximum length of that shape? Same thing with the infinity norm of A. It's the sup of the infinity norms of the outputs over the infinity norms of the inputs. So you look at the infinity circle, the infinity norm circle, which is, after all, the box with side length 2. And we ask, if I take some, say, vector there, it ends up, I don't know, maybe here, and I want to know what's the ratio of this length to that length, and that's what we're looking at here. So again, it's a question of how stretched out do things become overall, comparing the outputs to the inputs. Now, just as we can compare the norms of vectors, we can compare the norms of matrices. In fact, the claim made in this exercise in Trefethen and Bao is the following. If you look at the infinity norm of a matrix, the ratio of this to this, you can understand it in terms of the traditional 2 norms. In fact, the infinity norm is bounded by a square root of n times the 2 norm, and it's an upper bound for 1 over square root of m of the 2 norm. So there's a relationship. If you can bound the 2 norm, you can bound the infinity norm. If you can bound the infinity norm, you can bound the 2 norm. So I'm going to show 3.3c in Trefethen and Bao, and 3.3d is very similar. So 3.3c is the right-hand side of that inequality. We're showing that the infinity norm of A is less than or equal to the square root of n A2. Okay, so all we have to do here is use the definition. The infinity norm of A, by definition, is a supremum over all outputs AX in the infinity norm as a vector over the corresponding input infinity norm. Now here's the thing to keep in mind. Remember that A is m by n. So x is an n vector and ax is an m vector. I can manipulate the top and bottom of this fraction using the bounds that we already have for vector norms. In particular, the numerator can become bigger if I replace the infinity norm with the 2 norm. Remember, the infinity norm is less than or equal to the 2 norm. In fact, that's simply saying that if you have a vector on the circle, it fits in a smaller box than the circle itself. Anyway, the denominator can become smaller if I replace x, the infinity norm of x, with 1 over the square root of m times the 2 norm of x. So this was the second part of 3.3. This is 3.3b. Notice this is an n because actually x is an n vector, not an m vector like I wrote before, because here, to be in the domain of A, it must be an n vector. Now, if you just look at this for half of a second, you see what happens. Square root of n comes out as a constant. This should be inequality, right? And there we are. So because we can compare the inputs and outputs to themselves between the different norms, overall the matrix norm has a similar bound coming from that sort of relationship. To do 3.3d, you do the same exact procedure, set up the 2 norm, and compare it to the infinity norm using the opposite version of those two inequalities. So that's exercise 3.3 into Featherman Bow, and hopefully it gives a little bit of insight to how matrix norms work.